All right. So, are you going to introduce us? Okay. So I'm Saptarshi, Ben, Stephanie, and as you know, we got tired of reciprocal space, rings and dots, so no more Bragg's law, I hope. So we are doing imaging, so neutron imaging. So just to give you an idea of when it started, so 32, 33, Chadwick discovers neutron, and we have the first imaging started by Coleman and Kuhn a few years later. And the first radiograph at Oak Ridge was taken somewhere in the early 70s. And you can read through these. A lot of work has been done since then. So why neutrons? I guess we have found the answer already. But for imaging, we want to look at the neutron absorption cross-section, which in this case, you want to play the video? We can see some differences between isotopic absorption cross-section, between deuterium and hydrogen. In this case, this is a coffee pot and brewing coffee. And as you can see, the handles and the water contains hydrogen, which can be seen pretty visible, whereas the glass is not. So this is a difference between the neutron absorption cross-section. In similar ways, we can also talk about different metals which are used for construction, which are very transparent to neutrons, but other elements are not. So this gives us a pretty good advantage over X-ray. We can look into deeper sample sizes. Let's just get over. So everyone talks about Bragg, so we are going to talk about Beer-Lambert. So this is Beer-Lambert's law for transmission. And you can see that the transmission depends on the attenuation coefficient and the thickness of the sample. And also the attenuation coefficient is dependent on the density of the material cross-section, absorption cross-section for neutrons, and Avogadro number and molar mass. As Ben will talk about later about the sample we are studying, there is a absorption cross-section difference for the different metals we are studying. So this table is very important, and Stephanie will talk about the instrumentation.
So what's the line look like? So it's over at Heifer in the cold guide hall. And so neutrons come in this beam. It's filled with helium so that the neutrons don't interact with air. We don't want hydrogen around. And eventually they hit the sample and go to the detector. The sample and the detector are as close as they can be to improve spatial resolution. So once they hit the scintillation detector, light is emitted, bounces off the mirror, and goes down to the CCD detector down here. This mirror and the CCD detector angle is important so we don't ruin the detector. This fencing is very important so that users don't get affected by neutron radiation or gamma radiation. And so you can't have 5 millirem outside of that fence line. But as Ben's going to talk about, we are going to do a new sample setup at the line, and so we need to see what the open beam is like and what the radiation is like. So we were able to see the safety precautions that take place when they have a new type of experiment going on. And unfortunately, with our open beam, we did get 5 millirem outside of that fence line, so we had to push back that caution area with ropes. So what all can we do at the line? We can do control temperatures anywhere from cryogenic temperatures up to 1500 degrees Celsius. Time result imaging is made possible. As an example, this is a fuel injecting sample. We can do tomography, and our scan time depends upon our aperture, which we can control, so we can have a large one or a small one, and that kind of reflects back to our resolution. We have an 80 micron detector limit, but we can go up to 20 microns if we want to, but we lose a lot of resolution as a result of that. So now that we've seen what the detectors look like,
so I'm Ben, who currently going to be talking about a number of things. So let's get to the meat of the matter of what we're planning to do with this. So it was really nice for this experiment is this was actually a researcher who was visiting from UC Riverside who was working on high entropy alloys. So high entropy alloy, for those people of you, and tell me if I'm wandering too far away from the microphone, is an alloy that has roughly 5 or more different metallic elements in them in roughly equiatomic ratios. Now this as a whole, to be additionally a high entropy alloy, must form a very solid solution type matrix without a variety of intermetallic phases. This leads to a high configurational entropy and hence the name high entropy alloys. There should be a little caveat in there if there's some variation in the definition of high entropy alloys, but this is a generally accepted one. Now the nice part about these alloys of having this very high entropy and this solid solution type structure is they have a number of desirable properties. They can get good wear resistance, good fatigue resistance, and pretty high strength compared to if you just take one alloy and stick it, one element, stick it in another element to form an alloy, and just get that combination. Now, given that you have 5 or more things, and you think of all of the different metals that you have on the periodic table, that's a large domain space to be searching. So people really want to do this computationally, and this is involved in a field in material science known as integrated computational materials engineering, and because we all love acronyms here in the government, we'll call it ICME. So to get in that direction, we need to know some general properties of how these behave, which was the focus of this research. So specifically, we were looking at something that wasn't a high entropy alloy, namely cobalt, chromium, copper alloy, again in roughly equiatomic potentials, which being less than 5 different elements is not an HEA. But it has a nice property that high entropy alloys have, namely you can get a phase separation within the liquid phase. Now ideally, I'd have a ternary phase diagram, and even more ideally, you all would have virtual reality goggles so you could play around with the 3-dimensional phase diagram. But I'm pretty sure that the DOE was not going to fund that for all of you guys, being it would cost tens of thousands of dollars. So instead, we have this representative phase diagram that show what happens. So if you get to a high enough temperature, you're in a single liquid phase. However, if you're reducing the temperature, it breaks into 2 liquids with different compositions. So in specific for the system that we're working with, you get a copper-rich liquid phase, and then you get a cobalt-chrome-rich liquid phase. Now the nice part about this is, as you can see from the element absorption cross-section for neutrons, units and barns, copper is much, much smaller than it is for cobalt. So you get some pretty nice phase contrast in the system, allowing you to use neutron scattering. The ideal behind this is if we can model this simple system and see what's happening, and we know this is going to happen in higher entropy alloys, we can then take this and start applying it to when I have 5 different alloying elements, or 7 different alloying elements, or 11 different alloying elements, as opposed to jumping there from the start. So specifically, what we first did is after we got rid of the background and such, and took our little sample, which is the button head that's being held right there by Nick's hand with tweezers, we optimized the aperture size to get a balance between the resolution that we were getting and the scan times. And it turned out the optimum for this was about an 8.2 millimeter aperture, as you can read there, and a scan time of 40 seconds. With this, we then proceeded to program the computer to run scans across a range of different temperatures. So Nick, specifically, chose 2 temperatures which were less than the melting point of this copper-rich phase, a temperature that was in between the melting point of the copper-rich phase and the non-copper-rich phase, and then something that was floating around the melting point of the entire system to see what's happening as we transition up the temperature there, which Stephanie will talk about.
So before they melt, or I guess we help melt these samples, we saw our alloy right here. If you look really closely, I know it's dark, but you can see a little bit of a lighter structure right there. That is our copper-rich phase. The darker part is more of our cobalt, less transmitted. And so once we heat it up, we can see the copper phase start to melt a little bit. It's moving around. It's starting to flatten out. Once both phases have melted, we can see this little bubble at the top and little lighter images on the side, saying we do have liquid-liquid phase separation. So what does this mean? It is possible to achieve liquid-liquid phase separation in this type of experiment, and the little bubbles that we get are likely a copper-chromium precipitate. we can get phase separation during solidification. So we didn't show the process, but we also cooled the sample back down afterwards. And we could see the liquid move where the copper would end up on top and start to solidify as we cooled the sample down. We can see differential phase melting with different temperature scans at various speeds, various apertures as well. And it was a little bit better when we put two little pellets in at the same time. Again, you can see the phase separation much better at the bottom once they're both melted. But what does this mean in the long term of research? This means that this study allows us to, or this type of study can be used for more realistic in situ casting. And so we can look at true high entropy alloy systems and potentially have better, stronger materials.
We would, of course, like to acknowledge the scientists who are involved in this research and let us kind of muck around with some of their stuff, namely Lou, who works here as one of the beam scientists, and Nick from the University of California, Riverside. I'd like to thank all of the people who helped make the NX school possible for all of their long work, and I'm assuming there's going to be long work coming up soon, preparing for the next year. To all of you for your attention, and apparently to Nick's cats right there for helping him cope with jet lag, whose names are?
They are Natalia and Sarah.
There we go. And we'd like to thank all of you for listening, and if you have any questions, we'd be more than happy to take them at this time. Don't wait for it to stop. Yes?
This might not be a fair question since it was a user's experiment. It seems to me a flat plate geometry might have been better than a cylindrical geometry.
This is very true. This is in fact one of the first things we talked about is ideally, so when you get spinoidal decomposition, you have this kind of mishmash interweaving of networks, which is ideal to see in a flat geometry. You have thinner profile, and it's harder for the different liquid phases to get on top of each other. Their explanation of why they weren't doing that is that they want to do it in the future, but it's hard to make a crucible of alumina that's shaped like that, and so they're holding off on it for the moment. So yes, it is the ideal, but it was not what they're using.
You could just buy it.
Okay, well this is what we were given. So yes, that is the ideal, but yes.
Was there any talk in this situation of cooling faster to see, quenching it in order to see if those liquids would freeze and solid?
Yes, they definitely want to quench it. It would probably have to be done ex situ, so you'd make a material, you take it up to temperature, rapidly quench it, and then take it in and run a scan on it and see what's happening there to get those effects.
So one thing I forgot to mention was that most experiments take about 1 to 5 days to really complete. And so in order to be able to do that part of the experiment too, we would have needed a lot more time.
Do you guys have the value of the resolution that those images have?
Those will be, so those weren't at the optimal resolution. Well, it's a very sensitive microphone. Those weren't at the optimal resolution because that would have taken much longer to do an individual scan. When we were doing individual scans, it was about 40 seconds. Optimal resolution, which would have been 80 microns, would have taken on the order of 10 minutes per scan, something like that. And we were doing 5 pictures for each temperature profile, so you can do the math there. We did not get an exact resolution, but above, like larger than 100 microns. So.